welcome to the 7th lecture of module 1, which is on diffusion mass transfer. So, before going to this lecture, let us have recap on the previous lecture what we have discussed. In our previous lecture, we have considered the diffusion coefficient measurements and predictions. First, we have considered the gas phase diffusion coefficient measurements. As we have discussed that there are several methods available to measure the gas phase diffusivity, but we have considered only two simple methods to determine experimentally the gas phase diffusivity. One is the twin bulb method, and the second one we have considered is Stephan tube method. So, for both the cases we have obtained the governing equations to calculate the diffusivity from the experiments, and we have explained both the methods with relevant examples. So, in this lecture, we will continue with our discussion of gas phase diffusivity prediction by different correlations available in the literature. In this lecture, we will consider gas phase diffusivity prediction and then we will consider liquid phase diffusivity measurements and liquid phase diffusivity prediction. Let us consider the first case, gas phase diffusivity predictions. Although there are several experimental data available for different gaseous components, there are many components which are required experimental data or shortage of experimental data. In those cases, instead of experimental data, we can use the empirical correlations by which we can determine the diffusivity of the gas phase components. A very simple and reasonably accurate empirical equations which was suggested by Fuller, Skettler and Giddings in 1966 for binary gas phase diffusivity, up to moderate pressure. Say up about 20 atmosphere. The correlations they proposed is diffusivity of component A to diffusivity in B is equal to 10 to the power minus 7 T to the power 1.75 divided by P t into summation over V a to the power 1/3 plus summation over V b to the power 1/3 whole square multiplied by square root of 1 by m a plus 1 by m b, and the unit in meter square per second, where T is equal to temperature in Kelvin, m a, m b, these are the molecular weights of A and B, P T total pressure in atmosphere, V A and V B are the atomic diffusion volume in meter cube. So, the diffusivity obtained from this relation is in meter square per second. Now, let us take an example to calculate the diffusivity from this correlation. For example, for mixtures of carbon monoxide and hydrogen, predict the diffusivity using Fuller et al. 1966 formula for the following conditions. The first one is at 1 atmosphere pressure and 100 degree centigrade temperature. The second problem is at 2 atmosphere pressure and 100 degree centigrade temperature, and the third one at 1 atmosphere pressure and 200 degree centigrade temperature. So, let us consider the first one at 1 atmosphere pressure and 100 degree centigrade temperature. We know that diffusivity DAB will be equal to 10 to the power minus 7 T to the power 1.75 divided by P T summation over V a to the power 1/3 plus summation over V b to the power 1/3 whole square and into root over 1 by m a plus 1 by m b. So, the atomic values can be obtained from textbook. Let us consider A is equal to carbon monoxide and B is equal to hydrogen. Now, summation of V a would be 1 into carbon plus 1 into oxygen. So, this will be equal to 1. The molecular volume of carbon is 16.5 plus for oxygen it is 5.48. So, it will be equal to 21.98 and molecular weight of carbon monoxide Ma would be 1 into 12 plus 1 into 16 would be 28 kg per k mole. Similarly, for molecular volume for Vb would be 2 into hydrogen, 2 into molecular volume 2.31, it is 4.62, and Mb is 2 into 1 is equal to 2 kg per k mole. The temperature is given as 100 degree centigrade is equal to 100 plus 273 this much Kelvin. So, 373 Kelvin, and Pt is given 1 atmosphere. So, if we substitute DAB would be equal to 10 to the power minus 7, 373 temperature to the power 1.75 divided by 1 pressure into molecular volume of A is 21.98 to the power 1/3 plus for hydrogen 4.62 to the power 1/3 whole square into root over 1 by 28 plus 1 by 2 meter square per second. So, this will give you 1.159 into 10 to the power minus 4 meter square per second. Now, let us consider the second problem. That is at 2 atmosphere and 100 degree centigrade temperature. So, for this case, since we have already determined for the same system the diffusivity at a particular temperature and pressure, there is no need to calculate the diffusion coefficient for the same system at different conditions from scratch. So, we can use the diffusion coefficient determined in the earlier problem and calculate with respect to the temperature and pressure corrections. So, keeping all the properties same for the components in problem 2, at constant temperature, which is temperature is 100 degree centigrade, remains same, the diffusivity DAB from the Fuller's equation is inversely proportional with the total pressure. So, we can write at that temperature it is inversely proportional with pressure. So, we can write DAB1 or DAB2 by DAB1 will be PT1 by PT2. So, in this problem we can write DAB2 will be equal to PT1 by PT2 into DAB1. So, PT1 is 1 atmosphere, PT2 is 2 atmosphere, and DAB we have obtained 1.156 into 10 to the power minus 4 meter square per second. So, we can calculate D AB2 is equal to 1 by 2 into 1.156 into 10 to the power minus 4 meter square per second, which is equal to 0.58 into 10 to the power minus 4 meter square per second. So, for the third problem, similarly, since the temperature T2 is given as 200 degree centigrade temperature and PT2 is 1 atmosphere, which is remains same for the first problem. So, we can write DAB is directly proportional to the T to the power 1.75. So, we can write DAB2 by DAB1 will be equal to T1 T2 by T1 to the power 1.75. T2 is given as 200 plus 273 is equal to 473 K, and DAB1 is 1.159 into 10 to the power minus 4 meter square per second, and T1 is 100 degree centigrade, which is 373 Kelvin. So, DAB2 would be 473 by 373 to the power 1.75 into 1.159 into 10 to the power minus 4 meter square per second, which will be about 1.761 into 10 to the power minus 4 meter square per second. So, this is at different conditions for the same systems. There is another important useful correlations, which is Chapman-Skok equations. In this case, the equations is derived based on the kinetic theory of gases, and the diffusion coefficient calculated from these equations is strongly dependent on binary interaction parameters of the mixture pair. So, the equations which is given DAB is equal to 1.858 into 10 to the power minus 7 T to the power 1.5 divided by PT sigma AB square omega d into square root of 1 by MA plus 1 by MB. This is in meter square per second. Here T is the temperature in Kelvin, MA, MB are the molecular weights of A and B, PT is the total pressure in atmosphere, sigma AB is the characteristic length of binary mixture in angstrom, This we can calculate using sigma A plus sigma B divided by 2, and omega d is the collision integral which is a function of k t by epsilon a b. This epsilon a b can be calculated from root over epsilon a into epsilon b. Now, let us take an example, very simple example of mixture of ammonia and hydrogen. For this, predict the diffusivity using this formula at 1 atmosphere pressure and 100 degree centigrade temperature. Now, let us consider A is ammonia. So, Ma is equal to NH3 is equal to 17, and Mb is hydrogen is 2, T is given 100 degree centigrade. So, which is equal to 100 plus 273. So, 373 Kelvin, and Pt is the total pressure, which is 1 atmosphere. Now, the Lennard-Jones potential parameters. We can calculate for ammonia from the literature. We can, from the textbook, we can get 2.900 angstrom. So that we can calculate epsilon A by K is 558.3, and for hydrogen sigma B is 2.827 angstrom, and epsilon B by K is 59.7. So, using this value for this ammonia hydrogen pair, for NH3 which is A and H2 which is B, this pair, we can calculate sigma AB, which is sigma A plus sigma B by 2 is equal to 2.900 plus 2.827 by 2 is equal to 2.8635 angstrom. So, epsilon A B by K, we can obtain epsilon A by K epsilon B by K to the power half. So, it will be 558.3 into 59.7 to the power half is equal to 182.6. So, with this value Kt by epsilon AB will be 373 by 182.6 will give you 2.04. With this value from the collision integral, we can calculate omega d, we can obtain 1.075. Now, if we substitute all these values in the equation DAB, will be 1.858 into 10 to the power minus 7. T is 100 degree centigrade, is 373 to the power 1.5 divided by 1 into 2.8635 square into 1.075 multiplied by root over 1 by 17 plus 1 by 2. So, this will give 1.134 into 10 to the power minus 4 meter square per second. Let us consider another technique for liquid phase diffusion coefficient measurements. There are many methods available to calculate the liquid phase diffusivity. One of the simplest method is known as the diaphragm cell method. In this case, a simple cell is divided into two parts with a diaphragm. These diaphragm are the porous in nature, and in two compartments, compartment 1 and compartment 2, we can take two different concentrations of the liquids and allow them to diffuse between the compartments. After certain period of time, take the sample from different compartments and analyze, and then from the mole balance we can calculate the diffusivity. The assumption is that one very dilute solution is placed in compartment 1 and relatively little lower concentrations are placed in compartment 2, and molecular diffusions take place through the diaphragm. Let the volume of compartment 1 is VA1 and the concentration in compartment 1 is CA1, and the volume of compartment 2 is V2 and the concentration is CA2. Both the compartments are well mixed. Let the area of diaphragm is A and porosity is epsilon. So, effective area for diffusion is A epsilon. The diffusion path is not uniform. So, to account the non-uniformity of the diffusion path, we can use a term tortuosity factor tau. Tortuosity factor tau. Since the solute concentration is very low, solute concentration is very low. So, the bulk flow term can be neglected and taken as 0. So, in that case we can write the flux equation Na will be minus DAB dCA dH, which is equal to Ca1 minus Ca2 divided by H2 minus H1 into tau, which is equal to DAB Ca1 minus Ca2 by x tau, where x is equal to H2 minus H1, the thickness of the diaphragm. So, we can write the flux equations for both sides of the diaphragm. For compartment 1, it is V1 dCA1 dt would be equal to A epsilon Na, and for compartment 2 will be V2 dCA2 dt is equal to A epsilon Na. So, combining these two equations, we can get d Ca1 minus Ca2 dt would be equal to A epsilon dAb by x d tau Ca1 minus Ca2 into 1 by V1 plus 1 by V2. So, if the initial concentrations are between the compartments Ca1 0 and Ca2 0, then with the following conditions at t is equal to 0, Ca1 will be Ca1 0 and Ca2 will be Ca2 0, t is equal to Tf, Ca1 will be Ca1f and Ca2 will be Ca2f. Using this condition, we can integrate the flux equations and it will give d A b will be x d tau by A epsilon T f 1 by V 1 plus 1 by V 2 inverse ln C A 1 0 minus C A 2 0 divided by C A 1 f minus C A 2 f, which we can write 1 by alpha T f ln C A 1 0 minus C A 2 0 divided by C A 1 f minus C A 2 f, where alpha is the cell constant which is equal to A epsilon by x d tau 1 by V 1 plus 1 by V 2. So, this can be determined, alpha can be obtained using a solute of known diffusion coefficient. Now, let us consider a simple example. To measure the diffusivity of acetone in water at 20 degree centigrade, a diaphragm cell is used. Initially, compartment 1 of volume 50 centimeter cube is filled with 0.5 molar acetone in water, and the compartment 2 of volume 55 centimeter cube is filled with water. The molar concentration of acetone dropped to 0.4 molar in compartment 1 after 40 hours. The cell constant is given as 0.3 per centimeter square. Calculate the diffusivity of acetone. So, the data which are given is volume of compartment 1 is 50 centimeter cube, and for compartment 2 is 55 centimeter cube. TF total time, which is 40 hours, is 40 into 60 into 60 seconds. So, it will be 14400 seconds. Alpha cell constant is given 0.3 centimeter minus 2. At t is equal to 0, Ca1 naught is equal to 0.5 and Ca2 naught, because of pure water it is 0, concentration of acetone is 0. At t is equal to Tf, Ca1f is 0.4 dropped in compartment 1, and Ca2f we have to calculate from the material balance. So, if we do the material balance, V1 Ca1 naught plus V2 into Ca2 naught will be V1 Ca1 F plus V2 Ca2 F. So, 50 into 0.5 plus 55 into 0 will be equal to 50 into 4 plus 55 into Ca2f. So, Ca2f is equal to 0.091. So, then diffusivity DAB we can use 1 by alpha Tf ln concentration of Ca1 naught minus Ca2 naught by Ca1 F minus Ca2 F. Now, putting the value 1 by 0.3 into 144 naught seconds ln 0.5 minus 0 divided by 0.4 minus 0.091. So, this will give 1.11 into 10 to the power minus 5 centimeter square per second. So, which is equal to 1.11 into 10 to the power minus 9 meter square per second. There is some empirical correlations available to determine the liquid phase diffusivity, and one of the simplest correlations, which is known as Welke-Chanc equations, and it gives DAB is equal to 1.173 into 10 to the power minus 16 pi mb to the power 0.5 into T divided by mu b V a to the power 0.6 in meter square per second. Here DAB is the diffusivity of solute A in B, solvent B. Phi is the association factor. Mb is the molecular weight of solvent B. And T is the temperature in Kelvin. Mu b is the solution viscosity in kg per meter second. V a is the molar volume. At normal boiling point in meter cube per k mole. So, let us consider simple example to predict the diffusivity of acetone in water at 20 degree centigrade using Welke-Chanc equation. The association factor for water is given 2.26. The molar volume of acetone is given 0.074 meter cube per k mole, and the viscosity of water at 20 degree centigrade is 1.002 into 10 to the power minus 3 kg per meter second. So, using these values we can calculate DAB will be 1.173 into 10 to the power minus 16 into phi mb to the power 0.5 into T divided by mu b V a to the power 0.6. The temperature is 20 degrees centigrade, which is 20 plus 273 Kelvin. So, 293 Kelvin. So, if we substitute DAB would be 1.173 into 10 to the power minus 16 into association factor phi is given 2.26 and mb is 18 for water. So, substituting 2.26 into 18 to the power 0.5 into 293 divided by viscosity is given 1.002 into 10 to the power minus 3 multiplied by the volume, molar volume is given 0.74 to the power 0.6. This will give 1.04 into 10 to the power minus 9 meter square per second. There is another correlations which is Stokes-Einstein equation, which also says that the liquid phase diffusivity for different components varies linearly with absolute temperature and inversely proportional to the viscosity of the medium. So, we can write DAB mu by T is constant. So, this is end of lecture 7, and in the next lecture we will continue diffusivity for the multi component mixtures. Thank you.